Okay, so today's announcements, guys. I'm a little bit sick right now, so I'm trying to, guys. Okay, I can't really shout over people right now. Okay, so the Chapter 7 sapling is due 9 a.m. Monday still. I set the due date for that. Hopefully it should be visible. I do have like half a page left of Chapter 7 still to cover, but I figure we've covered enough that you can still do the entirety of the sapling. Here we are. Okay. All right, so just to wrap up what we were talking about last time with stereochemistry of reactions, we saw there's 3 different categories that you can fit reaction stereochemistry into. So just to do a quick summary of that here, 3 outcomes. You can either do syn addition, where both new groups add to the same face. So in other words, the 2 new groups are going to be cis to each other. So an example of that would be this with hydrogen and palladium on carbon. Both the new H's are going to add on the same face. So either both the methyls would end up bold. Actually, I'm going to add 1 extra carbon to that group for reasons that'll become clear later. So if I got a methyl and an ethyl on there to start out with, either both those groups are going to become bold, and the H's are going to add on dashed from the underside of the ring, or both the H's are going to be bold, and the 2 alkyl groups are going to get dashed. Okay. So this is one example of a syn addition. Kind of the telltale for that in the mechanism is whatever the groups are that got added, they have to get added from the same direction at the same time. Okay, the other category we covered, or one of the 2 others, is anti-addition, where they add to opposite faces. Or in other words, they're trans to each other. So if I do, say, this with Br2, I could either get bold bromine here, dashed bromine there, and then the methyl group just takes whatever place is not spoken for. Or dashed bromine here, bold bromine there, and then again the methyl takes whatever position is not taken on that carbon. Okay. And then the third possibility is random stereochemistry, which is going to be a mixture of both. So for example, HBr and peroxides could give bold bromine, bold H dash bromine, or dashed H bold bromine, or bold H bold bromine, or dashed H dash bromine. Okay, so you're going to get up to 4 different possible molecules out of this. Okay, so a few kind of big picture kind of warnings about this before we move on. One is that if you want to make absolutely certain that, for instance, syn addition is giving you both groups bold or both groups dashed, The caveat is that you have to draw the molecule in the same layout and same orientation, same conformation as it was in the starting material. Okay, so an example of when to watch out for that is, say I give you this alkene here, which is not cyclic. It's got an alkene in the middle. And I'm going to say, okay, I'm going to add, actually, let me tweak this a little to make it easier to see. Okay, I'm going to do cis-2-butene here. I'm going to say Br2, which should give me one bold, one dashed. And of course, the other way around too. Okay. The problem is, since I'm not looking at rings anymore with this molecule, I can really mess with you just by rotating this around the double bond. So I could redraw this. Scooch down here. If I want to pivot around the middle bond, what if I do dash bromine here and dash bromine there once I've spun the right half of the molecule 180? All right, so this is actually the same kind of trickery that we saw when we were looking at is something meso or not. Remember that when it's not cyclic, it's freely rotating around all its single bonds, and it may not be in the same conformation as you're expecting. So if I give you this and say, like, show the alkene that you would make this from as a result of dihalogenation, you're like, hold on, I can't do dihalogenation and get both bromines dashed. That's not possible, assuming that it's shown in the same conformation. So I would have to look at this and say, okay, working backwards, I got to pivot this around so both my bromines are like one bold, one dashed. And then that would give you that up there, and then you would tell, okay, I must have started with the cis alkene. Okay, and then just to finish it up, the same for this thing. Swiveling this around its middle gives bold bromines on both sides. Okay, so that's one thing to watch out for. Okay, questions about that topic? So I guess this is why we introduced this whole thing after we've covered rings, because at least rings are not going to screw with you by like pivoting around and changing their stereochemistry appearance. Like they're kind of locked in place, not like these acyclic alkenes that I just showed. Okay, so one last topic from this chapter that we got to cover is what's the relative amounts of the different products that we're getting for each of these kinds of reactions? Because we're getting multiple different products. How do we tell, like, is one more favored than another, or what's major, what's minor? Okay, so stereochemistry and reaction outcomes in general. We know that two enantiomers have the same energy as each other, the same heat of formation, all the same physical properties. So in a chiral environment, so in other words, there's no chiral molecules floating around or interacting with our reaction at all. Enantiomers are going to get produced in equal amounts. All right, so if I have a mixture of two enantiomers in equal amounts, what's that called? Racemic, right? Yeah. So, put this down here again. So this is actually why I turned this group into an ethyl instead of a methyl. What's the relationship between these two molecules right now? Yep, they're enantiomers. They're mirror images. If I'd left the methyl on there, that'd actually be the same because then you could flip it over but replacing this one so it's a different group actually fixed that for me. Okay, so these two are enantiomers of each other. And then we want to check, okay, is there anything written on anywhere on the arrow or the starting materials that's a chiral molecule? Generally, unless we're explicitly giving you chirality of something, like these things on the arrow, you can assume it's achiral unless you know otherwise. So H2, that can't possibly be a chiral molecule, it's just two hydrogen atoms. Palladium on carbon, also we're going to assume is achiral, turns out it is. Is this molecule chiral? So it is not chiral. There's I guess you can slice it in half like in the plane of the board. But yeah, there's like no asymmetric carbons on this thing. And if you drew its mirror image, it would reflect into it. Okay, so all of these are achiral. So that means if we draw out the reaction products that are possible and they both happen to be enantiomers of each other, that tells us these are going to get produced in 50-50 mixtures. So what you'll see really commonly is people won't even bother drawing both. They'll just draw one possible product and then say racemic in parentheses. So they just say rack next to one of them. Okay. Another example, this one here, this starting material, chiral or achiral? Achiral, yep. Br2, we're going to assume is achiral. Again, it's just a diatomic. There's no possible way that could be chiral. Okay, is this molecule, what's the relationship between the two products? Enantiomers, yep, every stereocenter flips. So exactly the same deal is going on here. These are enantiomers. Everything was achiral to start out with. These should be getting produced as a racemic mixture. Okay. More complicated example. Are any of my starting materials chiral here, as far as I know? Nope. I see people shaking their heads, and those people are correct. This is still achiral. HBr is achiral. ROR is achiral. Assume this is all achiral unless you explicitly know otherwise. Okay, so all of this is achiral. But what's the relationship between all of my products? Like, there is no single relationship between them anymore. There's 4 of them. So these two are enantiomers. Remember that like 2 by 2 square that we had when we were looking at relationships between molecules? Those are enants. These are enantiomers. Everything else is a diastereomer. Oh, and that relationship too. Okay, so 2 enantiomers, like these two, for example, are still going to get produced in equal mixtures. So you're going to get some amount of a racemic mixture of like one of these guys. But you're also going to get, like, so these two are produced in equal amounts to each other. These two, also enantiomers to each other, they're going to get produced in equal amounts to each other. But any other relationship between them, we don't know how it's going to look. They're diastereomers, so they're probably going to get produced in unequal amounts. So equal amounts to each other, unequal amounts between pairs. Okay, so an example of numbers, maybe you'd get like, I don't know, just to throw some numbers on here, 20, 20, 30, and 30, for example. Like these two are still getting produced in equal amounts because they're enantiomers, but those amounts are different from the 2 equal amounts that are getting produced up here. I have no idea what the actual numbers are. That's just sort of an example. Okay, so that sort of takes me back to this. If they're diastereomers, they get produced in unequal amounts. Okay, so for example, actually, let me finish that sentence. So diastereos get produced in unequal amounts in anything that's produced from chiral starting materials. Or reagents. Is also going to be unequal. So basically, the only way to get a perfectly optically inactive sample, in other words, is to start out with everything that's optically inactive. Okay, so here's one example. I actually have a chiral starting material here. And I hit this with Br2. And I'm going to get bold methyl, dashed bromine, bold bromine, okay, bold bromine and dashed bromine. Okay, so you may have seen, if you can see around my torso while I'm writing here, I accidentally drew this methyl dashed at the start. That is a mistake. Do not do that. I was looking at the wrong part of my notes. But this methyl group, does this get affected at all by the reaction? Right, yeah, it's like totally out of the whole whatever is going on over here. So this methyl group starts bold and it stays bold the entire time. So this is unaffected by the reaction. So our methyl is always going to be bold, but the bromine, like always, can either add dashed bold or bold dashed, which means these two guys are what to each other? Yep, diastereomers, so unequal. And I saw your hand, give me just a second here. Okay, question?
Would the bromine want to add a lot more substituted carbon where the methyl group is?
Excellent question. It turns out people have put together a bunch of different ways to sort of try to model like which diastereomer is more favored than another. It turns out it's actually really hard to predict sometimes. And so we're not going to cover like predicting which one's more favored. We're just going to say unequal amounts. So, yeah, I'm actually, for this particular reaction, I don't know for sure what the answer would be. So,
Did you ever get like a reaction like this where you have an answer?
So that's a good question. I guess the problem is, so you mean like if you start with a chiral starting material? The problem is for all the reactions that we've seen so far, if an atom is chiral in the starting material, it pretty much has to not be part of an alkene. And that means since the reactions we've seen so far all affect alkenes, any chiral atoms on our starting material are not going to get involved directly in the reaction, and they're just going to stay the same the whole time. When we get into chapter 9, we're going to see reactions that happen at asymmetric carbons potentially, and then you can actually look at like, does this get changed or does it stay the same, or like what's the numbers on that look like? But for the time being, yeah, all of our asymmetric carbons are going to be unchanged by these addition reactions. Question in the back?
Do you think you could explain why each of the starting materials in the top problem are achiral?
Yeah, so if I drew the mirror image of this, let me actually hop over here so I got more space. If I drew the starting material for this, say I choose to show the mirror here, there's nothing stopping me from just like scooping up under this one, and I always like thinking of it as like flipping a pancake over, because there's nothing bold or dashed sticking into or out of the plane, and so there's nothing we have to worry about overlapping or not overlapping onto bold or dashed over here. Yep, or you can look at, like, if you're looking for the internal mirror plane of symmetry, you can just sort of picture, like, I don't know why I always think of cooking for this, but like if you're filleting a fish and it's sort of sitting flat on the cutting board and you're sort of like slicing along through the middle of the plane, you're sort of like doing the same thing and slicing this guy in half this way. And like all of these atoms are going to reflect like one half into the other half on the other side of that plane. Okay.
If there's no bold dash, can we pretty much assume that the molecule is achiral?
Yes, or at least like if it were chiral, you would have no way of figuring out like if it's R or S because, yeah, there's not enough information given. Okay, so just to sort of wrap up this topic here, kind of a good rule of thumb is optically inactive in gives optically inactive out. So that's kind of what we saw the first two reactions up here, actually for the third as well, because everything was optically inactive to start out with, and everything we're getting out of it is a racemic mixture and is optically inactive. The same for the third reaction here, everything was achiral and optically inactive, and even though we're getting a whole bunch of different crud going on as far as products, it's still some mixture of two different racemic mixtures, which means that it's still each of those racemic mixtures is optically inactive, so no matter what proportions they combine in, the whole deal is still going to be optically inactive. Question? Ah, excellent question. So for those who couldn't hear that, what if we do Br2 and say a chiral alcohol like, I don't know, let's do this one, which I guess would be R2-butanol. All right, so again, I could do one group bold and one group dashed. Okay. So this is looking a little bit wonky here, just because I'm trying to show two different stereochems going on. It might be a little bit easier if I show the methyl group, being the one that's out of plane over here. Okay. So again, you can go through and sort of double check, like this should have been R to start out with. Is this carbon of the alcohol getting impacted or changed by the reaction at all? So remember that when the whole thing happens, this ROH, this oxygen is the one that goes and attacks, and then later on the oxygen's H gets deprotonated. So this carbon, this whole deal over here is unchanged by the reaction. Okay, so we started with R. We should have ended up with R at this carbon. I just choose to draw the methyl bold instead of the O just to sort of keep things a little bit easier to keep track of. But I think if you build a model kit of this, it should look okay. Okay, so that's one possible outcome. And again, that's one possible outcome. So what's the relationship between these two products? Diastereomers, yeah. So equal or unequal amounts? Unequal, yep. Okay, yeah, so pretty much any way that we introduce chirality into the whole deal is going to end up giving us diastereomers. What's really cool, I'm not going to get super into this, but it's super useful and heavily taken advantage of in multi-step synthesis, which we'll cover a little bit later on, is you can actually do this with some molecules that don't permanently get incorporated into the molecule, like maybe they stick on temporarily, give sort of a handedness to the whole thing while the reaction's happening, like cause one molecule to get favored over another, and then drop off at the end. So These are called chiral auxiliaries, and they can be used to sort of favor one enantiomer over another, even if, you know, your final molecule like doesn't actually have that chiral group in there anymore. So there's a ton of research into this, and a bunch of really useful reactions that have been discovered over the past, like, what, probably 30 years that they've been working on it. The book has more details if you're interested, though. Sorry, I saw your hand first, I think.
Is the bromine in the first side stereomer bold? Is that?
This one, yeah, that's a bold. Sorry. Yep. Okay, and then I saw another hand. No? Okay, maybe I already answered. Oh, yeah.
How did you determine that those two were diastereomers instead of?
Yep, so like always, I want to look at every asymmetric carbon in the molecule and compare between, like, is it the same or flipped? So this one's flipped with the bromine, this one's flipped, but this one stays the same because we know this carbon doesn't get changed by the reaction. Like, it started R, it's going to stay R. So just because we're introducing some asymmetric carbon that's like a constant means that these two are no longer mirror images of each other. So, okay. Any other questions about this? Okay, cool. So that pretty much wraps it up for Chapter 7. Okay. All right, so sort of a quick note about how actually the entire rest of the semester is going to go for organization. I'll write it up here, actually. So Chapter 8's going to be naming a whole bunch of functional groups with heteroatoms. So you should know by now how to identify like an alcohol, an alkyl halide, stuff like that. So Chapter 8 is just going to go through a bunch of different functional groups one by one and talk about how to name them. And also talk about physical properties. And I think right at the end, actually no, never mind, sorry. In this edition of Loudon, they don't actually have any reactions at all in Chapter 8. Okay, so then the next few chapters after that, 9, 10, and 11, which is where we're going to end for the course, are just taking one or two of those functional groups per chapter and digging really hard into like what do they do for reactions, like how do we know, like how to use them as starting materials. So Chapter 9's going to be alkyl halides. Chapter 10 is going to be alcohols and a little bit of thiols. And Chapter 11 is going to be ethers and epoxides, mostly. Okay, so these three are all pretty reaction heavy. And Chapter 8 is sort of like a, let's introduce these functional groups and talk about them a little bit before we get into what they actually do. Okay, so Chapter 8 is fairly short and easy, but Chapter 9 is just like a whole ton of stuff about reactions for alkyl halides, which turned out to actually be like kind of a nice, convenient, simpler model to start looking at reactions of alcohols afterwards, because alcohols do the same thing just with a little bit more complications. Okay, so questions about kind of where we're going for the rest of the semester? Okay, also while I'm thinking of it, I'm not sure exactly how I want to compensate for missing 2 days due to snow yet. I may end up trimming stuff out of the end of Chapter 11, or I may just like drop all the thiol stuff out of 10. But I'm going to sort of play it by ear and see like how far behind we are as we get to that point. So, okay. So let's get into Chapter 8. Okay. So just as a quick refresher in case you don't remember what those look like, alkyl halides are anything with a bond between an alkyl and a halide, obviously. Alcohols are anything with an alkyl group with an OH on it. Ethers are two alkyl groups on either side of an oxygen. Okay. So we are also going to look a little bit at thiols, which are pretty much the same as alcohols, just with a sulfur, which is right below oxygen in the periodic table. They do pretty similar chemistry to alcohol, but if you remember, like the atom effect means that they're more acidic. Plus, they can violate the octet rule on sulfur. So they're going to do a little bit of extra stuff just by virtue of having a different atom there. And then we can also look at sulfides, which are pretty equivalent to ethers. Again, with an S there instead. Okay. One last functional group that's sort of, I guess, like a combo functional group. That is two or more OHs on adjacent carbons are called glycols. So an example of that would be this one, which is commonly named ethylene glycol, which gets used for antifreeze quite a bit. Problem is that it's also poisonous to pets and it tastes sweet, which is a bad combo. So sort of a more safe version of this is one with an extra methyl group on there. This one is propylene glycol. Okay, so that one is not poisonous. I don't know how it tastes though. Someone else can report that. No. Okay. So we're going to look at sort of these functional groups one by one. And look at how to name them. And the problem is that for both of these, we're going to look at first the non-IUPAC name, the pre-IUPAC like old name, and then also the IUPAC name. So we're going to have to see two different naming systems for all of these, unfortunately. And that's because a lot of them have sort of names pinned onto them before IUPAC really got into the picture. Okay, so nomenclature here. So let's start out with alkyl halides. So the common name is whatever the alkyl group is plus whatever the halide is. So for example, this one, the alkyl group is ethyl, the halogen is chloride, so ethyl chloride. This one, it's got a butyl group and an iodide, so butyl iodide. Okay, so pretty simple and easy. Just as a quick reminder here, we're going to see a lot of those two-letter abbreviations for alkyl groups pop up again. So another way that you might see ethyl chloride here is ETCl, ethyl chloride, or BUI, butyl iodide. So definitely brush up on those group abbreviations if you're not comfortable with them. We're also going to see a couple of the groups that got introduced during the alkenes chapter. What's the name of this group, if you guys remember? Allyl, yep. So I could do like allyl bromide, or I could do vinyl chloride. Some that we haven't explicitly covered yet, I think, are aromatic rings attached to stuff. So this one, I haven't done fluoride yet. Okay. All right, so let's actually look at two new groups that I'm going to introduce here. One of them is an aromatic ring attached directly to whatever, and the other is an aromatic ring attached to one more carbon, a CH2 group attached to whatever. All right, so due to a historical mistake, this group is called phenyl, and this group, even though it's benzene plus something else, is called benzyl. So this would be phenyl fluoride, and this would be benzyl chloride. Okay, question in the back? Yes, but they're not as frequently used. I want to say AL, maybe? And vinyl, I think if people abbreviate it, I think it's VN. I honestly don't remember off the top of my head because they're a lot less frequently used than the alkyl ones. I might have to look that up and get back to you. So these two, don't remember the abbreviations. These two do get abbreviated fairly frequently. Benzyl is BN. And phenyl is either PH, or when people want to get fancy, they'll actually use a phi. So phenyl fluoride. Okay. Which means that benzyl, because it's that with an extra carbon, could be phenyl CH2, and then whatever the halogen is. Okay. So, so I guess sort of the takeaway message from this part of naming is that so long as we have one of the easily named IUPAC, alkyl or simple like alkene or aromatic groups, common naming works totally fine. As soon as we get something more complicated than this, where we no longer have like a simple abbreviation we can pin on it, common just sort of doesn't really know how to handle it, and then we got to switch over to IUPAC, which we'll do in a second. Any other questions about this? Okay, so I'm going to erase the board real quick, but there is one more common name that I want to, or group of common names that I want to cover. Okay. So a couple more common names apply to things with multiple halogens. Guys? Okay, so some of these you're actually familiar with already because something with a carbon with an H and 3 halogens is called a haloform. And you use one particular haloform as a solvent for NMR, chloroform, or deuterated chloroform specifically. So carbon with 1H and 3 chlorines is chloroform. We can also do some other halogens, so like HCI3 would be iodoform, which interestingly is sort of a bright yellow powder that smells really medicinal, and it turns out is a pretty decent antibiotic. And so this was actually used really heavily in World War I in hospitals to disinfect a lot of stuff. Okay, couple more. This one, actually, CH2Cl2 is, of course, dichloromethane. Well, okay, so this is actually the IUPAC name for it, and we'll cover sort of like how we figured that out. Do you guys know the non-systematic name for that one? Yeah. So this is methylene chloride. Under the old common naming. Okay, and then one more that I really hope you haven't used as a solvent ever because it's not great for you, is carbon tetrachloride. Turns out it is actually a really good solvent for some reactions, but to be avoided if you possibly can. I think it's either carcinogenic or just very toxic. Okay. So any questions about the common names for these ones? Okay. Cool. So real quick, in the last few minutes that I got left, the IUPAC for these is super easy, and we've actually already covered it. We just treat the halogen as any other substituent. So, and note that we're going to drop the 1 if there's only one possible location for that. Sorry, I left a big smudge on the board here. Hopefully you guys can still read through that. So drop the 1 if there's no other option for the location. Okay, so this one under IUPAC we could call 1-chloroethane. But it's not possible to have a 2-chloroethane. Having the chlorine here is what makes this carbon number 1. So we're just going to call it chloroethane. However, here, we could have the iodine coming off of carbon number 1, or we could have it coming off of carbon number 2, and those would be 2 different molecules. So this one we do have to include it. 1-iodo butane. Okay, so questions about that? Okay, cool. So that's a good stopping place with alkyl halides. I'll do the next functional group on Friday.